Okay, so welcome back, my linear algebra babies. So with the preliminaries out of the way, we have some vocabulary to work with. Let's jump in and get started. So example one. So it says let matrix A be defined as follows. Let vector U be defined as follows. Vector B, vector C be defined as followed. And we are going to define a transformation from R2 to R3 by the following. T of x is equal to AX. So matrix A multiplied by some vector x. All right, now, this is a multiple part question. So let's start with part A. So it asks us to find T of U. So to find T of U. Now, T of U, so of course, let's go ahead and establish. In this case, U has been defined for us as 2, -1. T of U is just simply the image of U after or under the transformation T. All right, well, as I highlighted above, T of x is equal to A of x. So let's just use our transformation. So in this case, we're going to have T of U is going to be equal to A multiplied by vector U. All right? You can think of x as the set of all vectors. And so A, whereas U is just a specifically defined vector. So, all right, A times U. So here we go. Let's kind of speed this up a little bit. So matrix A, so that's going to be 1, -3, 3, 5, -1, 7, multiplied by U, which is 2, -1. Now, I'm not going to go through this multiplication. I've already done that in previous lectures. So let me get to the result. So the result is the following. 5, 1, -9. All right, so that's the image, right? That is the image of U under that transformation of T. Okay, so we're done. So now, if you take a look down below at the geometry of what's really happening here. So take a look. You start off, I mean, look, vector U is just some point in two-dimensional space, right? It's a point on our plane. And now through that multiplication of that matrix A, we were able to take that point and transform it into a point in three-dimensional space, right? 5, 1, -9. So this will be a little bit hard. I have a three-dimensional axis here, but I don't have access to the negative number. So it'll be a little bit harder to draw, but I think you can imagine where we would be going 5, and we would be going 5 this direction, then 1 this direction, and then we would be going in the negative direction of z 9 places. And all of that to say, what? That 5, 1, -9 is just a vector, but it is the image of vector U under T. So this is T of U. Ready? Let's go to the next one. Part B. So with part B, it asks us to find, now in this case, we're actually asked to find an x in R2, right? So looking at my xy, say xy coordinate system, if you'd like to think of it, x sub 1, x sub 2, there's some point in there. So we want to find an x in two-dimensional space whose image under T is B. Okay. So in this case, let's go ahead and establish. So the problem has told us that B is defined to be 3, 2, negative 5. All right, do you understand the question, right? That's a lot of linear algebra just comes down to, do you actually understand the question? Well, here is the question. So we have A, and we know what that is, multiplied by X, right? But it says in R2, so that would mean we have two variables. So A multiplied by some X has to equal B. Do you understand? I know what I know how the vector B is defined. I know how matrix A is defined. I just don't know which point in R2 is going to map me from to B. All right. Well, the good news is row reduction algorithms are here to save the day. So what we're going to do is we're going to take matrix A, and we're going to create an augmented matrix like so. So we're going to start with matrix A, 1, 3, negative 1. So that's negative 3, 5, 7. All right, now that is our matrix A defined. We're going to go ahead and use the fact that we're trying to map to vector B, and we're going to set up an augmented matrix 3, 2, negative 5. Here we go. So you know where we're going with this. We have set up our matrix. We're going to row reduce, and let's see what comes back out. So we have 1, 0, 0, 0, 1, 0, and then 1.5, negative, I believe that is 0.5, 0. Sometimes I can't quite read my handwriting. So what did we just figure out? Well, we figured out that x sub 1 is equal to 1.5, and we figured out that x sub 2 is equal to negative 0.5. So if I were to travel to the right, let's say, we'll say this is x, we'll say this is x1 and that this is x sub 2. If I were to travel to the right 1.5 and then down a half, here we go. This x is the one that we're looking for. Okay, so if you could always, again, if you're kind of second guessing yourself, just think about what you have available. You can always plug this vector, the x, back in, multiply by matrix A, and then see if you actually, in fact, do get matrix B. Okay? So what is the answer to that question? The answer to that question is the following vector. X, this is the x that maps, the x from R2 that maps to B under T. All right, let's go to part C. Okay. So part C. Now what's interesting is part C and part B are, you don't really have to roll your sleeves up much. Okay, these are actually very important questions, more important questions, I would argue, because it gets to the essence of this subject. So part B is actually a uniqueness question. Whereas part D, so part C is just a uniqueness question. Part D is actually an existence question. But let's jump in. Ready? So part B reads as follows. My apologies. Part C reads as follows. So I'm gonna cross out A. I'm gonna cross out B. We're done there. So it says, is there more than one x in R2 whose image under T is B? All right. Is there more than one x in R2? Well, look. So what you're seeing here is I've basically just copied and pasted the matrix after the row reduction, and we're going to use this to answer part C. Ready? So is there more than one x? Well, think about it. What would you expect to see at this stage right here if there were more than one x that you could have chosen to get to B? Well, you would expect to see free variables. And I don't see any free variables, right? We have x sub 1 is defined, x sub 2 is defined, but our basic variables are defined. And there's no free variables to work with. So that means that our solution, right, that this solution is actually unique. So let's go ahead and answer the question. The question is there more than one x whose image under T is B? And the answer is no. That's the only way for you to get from R2 to that point in R3. All right, part D. It says determine if C is in the range of the transformation of T. In the range, mean like, can you get there, right? Can you actually get to C? Now, you would approach part D exactly like we did in part B. Only now, instead of having that last column be vector B, our last column is going to be vector C. But again, what I'm really trying to highlight here is, does it exist, right? This is an existence question. Is it in the range of the transformation of T? Can you actually find some value in some point in R2 to map to that point? Well, let's go ahead and set everything up. So what we're doing is we're just going to take A times x sub 1, x sub 2. Only now we're going to set this equal to C. Ready? So we have 1, 3, negative 1, negative 3, 5, 7. And now we're going to take vector C, which is 3, 2, 5. And we're going to row reduce. All right. So here's what it looks like. So we have 1, 0, 0, negative 3, 1, 0, and 3, 2, and negative 35. Now, so I can't remember how I arrived at this. I don't know if I RREF'd this guy or if I just quickly went through the algorithm. But let's just assume it doesn't, neither here nor there, it doesn't matter. Where I'm at right now in this problem answers the question. So, but I want you to do me a favor. I want you to stare at this for just a second. I want you to put away your phone, put your life on hold for just a second, and come back to this truth, these knowledge bombs that I'm trying to give you here. I want you to look at that row reduced matrix, and I want you to tell me, is there a way that you can get to this point in space by choosing some point on a plane? Well, let's take a look. This is a problem, right? This is if you're using a calculator and you're staring at this on your calculator screen, your calculator is trying to tell you, hey, there's a problem, right? That little statement means I'm gonna I'm going to transform this. This would mean I'm going to take that last row. Okay, this is row 3. So I'm going to rewrite row 3 for you. So 0 x sub 1 plus 0 x sub 2 somehow is supposed to equal negative 35. That's a problem, right? How are you going to add up a bunch of zeros and arrive at the destination of negative 35? So what does that mean? What does that mean to the question? Well, what was the question? Determine if C is in the range of the transformation T. No, right? It's not. You can pick any point you want in that. You can pick any point you want in this whole plane. You are never going to be able to get to point C in space under that transformation T. So it is not in the range. All right. So I hope that little tutorial made sense. Let's just go ahead and continue. So example 2, it says we're going to let A be the following 3 by 3 matrix. And then the transformation, so this is just some notation for transformation. So then the transformation x to ax projects points in R3 onto the x1, x2 plane. Because, now I've kind of cut the question off here. So hold on for a second. So x to ax. So let's make sense of that for just a second. Well, we know that the setup looks like this. A times x normally equals some value b. But in this case, what I'm going to do, I'm going to forget about, I'm going to see what does the form of B look like. Right, that's my goal right now. So let me plug in. So I would have A is defined as 1, 0, 0, 0, 1, 0. Now, so this would be a 3 by 3 matrix. Now, structurally, if you want to be able to do this matrix multiplication, remember the vector x is going to have 3 rows, right? So we're going to have x sub 1, x sub 2, x sub 3. That's structurally, that's the only way you're going to be able to make this work. Now, if you were to go through and multiply this out, it wouldn't take you very long. But this is what I'm going to write now, is what you would expect your answer to look like, right? Just the general form. So what is it? Here it is. It would simply be x sub 1, x sub 2, 0. Now stop for just a second. I know we have defined an A, and I know that I have not given you an x to multiply by, nor have I given you a b, right? So of the 3 pieces, you only have 1. What I'm telling you is right now is this is what, if you had an x and did your matrix multiplication, this is the structure of the result. X sub 1, x sub 2, 0, and I just want you to think about just for a second, if you were to graph, right, the geometry of this, the geometric interpretation of this, what would you have? Well, I'm looking at the structure of B. Now, this is a 3 by 1. So normally I'm thinking, or not normally, but we should be thinking that we are in space. But we only have two variables. We have three variables. My apologies. We only our third variable is already defined to be 0. So in other words, we have length, we have width, but we have no height. So what do we have? Well, it makes sense. This figure 3 tells it all. You really have a plane. You have a plane that's nestled in space, right? The x1, x2 plane. And then what's happening is that now, if you can kind of look at the graph, what's happening is, if you kind of bear with me here, so here is some point. Let's call it, I don't care, let's call it Z. Z is some point in space. Now, after you multiply point Z by that 3 by 3 matrix A, notice how it just projects itself onto this two-dimensional plane, right? This x1, x2 plane in R2. So that's just some quick geometry of example 2. The math is, again, fairly easy. I think you would agree with me. Okay, so almost the majority of the transformations that we have done so far have all been, say, an R2 to an R3 or an R3 to an R2. But now what we're going to do is we're going to stick with the same dimension, right? So we're going to think about transformations from Rn to Rn, right? So that would mean an R2 to R2, say, transformation, right? The input is 2 dimensions and the output is 2 dimensions. Now, so example 3, I've written it here. I don't think it's actually on the handouts, but it's an example 3 says, let t of x equal a of x, and t be defined as a transformation from R2 to R2. All right. Then they tell us how to define matrix A, so that's a 2 by 2 matrix. They tell us how to define a vector u and how to define a vector v. And what you're going to see is, if you have ever enjoyed animation, you're gonna kind of see what we call a shear, SHEAR transformation, and it's just a way of adjusting the shape, as you can kind of see from some of the pictures that are here. So in this first graph right here, so this is let's say this is figure 1. I took the liberty of graphing vector u and vector v. Now, this is the original, right? No transformations yet. Now, our job right now is to go ahead and find t of u, t of v. And then we're going to replot those points here in, let's call it figure 2. And let's see how the points changed. Ready? So, t of u. So this would be a matter of multiplying matrix A, which is 0, 3, 0, 1. And we're doing t of u, so multiply that by u, which is 0, 2. And I'm going to go ahead and set up t of v as well. So that will be 0, 3, 0, 1. Now we will be multiplying by vector v, which is defined to be 2, 2. Okay, so what's our results here? Well, let me just go ahead and do the math. So if you multiply, if u undergoes the transformation t, we end up with a new vector 6, 2. And if vector v undergoes the transformation t, we end up with a new vector 8, 2. Ready? Let's graph these new vectors. So my apologies, I can't see very well. 1, 2, 3, 4, 5, 6. I don't think I have enough. So I'm going to do this in, or I'm going to have to zoom in. when you get older like me, your eye starts to go. So let me graph 6, 2. 1, 2, 3, 4, 5, 6, 2. Now this is t of u. And then let me move to the right 8, so I'll have to go out a little bit more. And then up 2. And now this would be t of v. Okay. So notice that we have some rectangular shape in figure 1, and now you can kind of see the shear. So actually, let me do that again because I should have been at 2. Try that one more time. Right? So that's the idea. That's the idea, and that's exactly what figure 4 is trying to show you. So that's an Rn to Rn transformation. Now, the definitions that are written here at the bottom of page 4, it basically what they're saying. Of course, so I'll go ahead and read them to you. So a transformation, right, or mapping, T is linear, right? It's a linear transformation if, well, T of u plus v is the same thing as T of u plus T of v. And now C means some scalar. T of cu is equal to ct of u. I'll make that come alive in just a second with what do I mean by linear transformation if those two conditions are met. But in reality, every matrix transformation, if you can remember this, every matrix transformation, every time you do AX equals, every matrix transformation is a linear transformation. Okay, now I offer you that without proof. The proof is not that it's not that hard to go through, but I offer you that statement. Every matrix transformation is a linear transformation, without the justification. Be careful that if you set that up as an if-then statement, you don't get to switch it. You can't make the statement that every linear transformation is a matrix transformation, right? So that is actually incorrect. But the former conditional is correct. So we're going to this is another if-then statement. If T is a linear transformation, then, well, now here, of course, I just want you to make sure this 0 means a 0 vector. T of 0 is 0, and so forth. I want to see if I can. I'm going to skip example 4. I'm going to go to example 5. I'm going to see if I can make sense of some of these definitions for you. So, example 5, it says we're going to define a linear transformation from R2 to R2 by the following. All right. So they have told us how to define our transformation T of x. Now our job is to find the images under T of u, v, and u plus v. So here we go. I'm down at the bottom. So if you want to find the images under T of u, that is the same thing as asking what is T of u. I'm going to stop there for a second. Do you see? Like, you can see how it can be frustrating for a young math student, because what we're about to do is actually fairly simple arithmetic and or in very simple structure, but the language, right? The language can sometimes prevent you from doing well. So find. So one more time. Find the images of t, or my apologies. Find the images under t of, and what you need to be able to do is translate that as saying, well, the images under t of u is simply t of u. The images under t of v is simply t of v, right? Just keeping track of your vocabulary. All right, so let's go through this really quickly. We have our definition. So in this case, we know A. This is the matrix A that we're going to use, and what I'm going to do for each one of these is just simply take matrix A and multiply it by, we'll start with U, then we'll take matrix A, we're going to multiply that by V, and then finally we'll take matrix A and multiply that by U plus V. Now U plus V is 4 plus 2 is 6, 1 plus 3 is 4. All right, you got to be careful if I rush too much, then well, I start making silly mistakes. All right, ready? So let's get to this result. If you go ahead and multiply these vectors by that matrix A, we're going to get -1, 4, -3, 2, and we're going to get -4, 6. All right, now come back to me. So here's what's interesting. So I mentioned animation not too long ago. So if this was, I don't know, let's just assume that you're doing some, let's just say you're doing some two-dimensional animation. Maybe you're, we have this little quadrilateral. Maybe you're making another version of Flatland, if you know that famous math movie Flatland. And what you want is this little guy to rotate, right? That's, in other words, the hero of your story is this beautiful little quadrilateral, and you want this guy to, well, you don't want him just to stand there, him or her to stand there all movie, so you want them to move around. So, well, notice how matrix A is a way of rotation. It's a way of rotating that quadrilateral. So if you were to plot the original vectors, then plot the new vectors under the transformation, you would see this rotation take place. And finally, on your own time, if you notice that T of U plus V is equal to T of U plus T of V, right? That is exactly what we were discussing earlier. It's the exact definitions of, or one of the criteria that needs to be met when we're talking about linear transformations. So, last question. Last question. So, I appreciate your patience. I know these. Well, the subject matter is sometimes impenetrable for many, or at least it feels that way in the beginning. And then I know you get tired, and I know you have other things going on. So I do appreciate your patience. So example 6. So I'm going to try to get to this as quickly as possible through. So we have an application question dealing with linear transformations. And what's really interesting, if you are thinking about doing some type of business major or double majoring, or maybe this is a business application, but maybe you can see this even if you're thinking about staying in the sciences. Notice how you can change the type of data. You can transform a certain type of data to another type of data using these matrix transformations. Ready? So it says a company, ready, let me read. So a company manufactures two products, product B and C. Okay? Now look, I don't know, let's say this is your company. I don't know what you're making. You only have two products. Let's just say, I don't know, you are in you make bacon. That's one thing you love to make at your factory. And you also make, I don't know, clocks. I don't know why you specialized in bacon clocks, but those are your two products. And ready? Let's go. So a company manufactures two products, B and C. Using data from example 7 in section 1.7, we construct a unit cost matrix. Now, in other words, this was all done for you. Okay, so continue. You don't need to, it's not required that you have to construct that unit cost matrix. So U is equal to the following. So this is I've kind of defined it down here too. A unit cost, that's just a cost per dollar, right? The cost per dollar of production. Now, whose columns describe, so now we're here. So the columns describe the cost per dollars of output for these products. Cost per dollar. So let's kind of look at your costs. You have to make your bacon and clocks. You got material, you got labor, and you got overhead. Now, it says let x, so that's your vector, let x be a production vector. Okay, a production vector. That's how much you, so you can think of production vector in, it's where, so let me, so where x sub 1 is the amount of dollars of production of product B, and x sub 2 is the amount of dollars of product C. Right? So, all right, well, let's see if we can at least make sense of that before we go any farther. So, x is some type of production vector, and where x sub 1 is the dollars that you spent on product B, and x sub 2 is the dollars worth of product C. So, right? So dollars worth of product B, dollars worth of product C. All right. Now, T of x, and on this, let me actually finish here. We're going to define, this is a transformation defined from R2 to R3 by the following, T of x. All right. So let's think about, so this is, so you can think about your unit cost matrix being set up as follows, right? So this can give you your total cost of materials, total cost of labor, total cost of overhead. This is actually really interesting. And my apologies, I wish I could explain it better. But what does T do for you, right? Why would you want to set up this function T of x? Well, what's really cool is it transforms a list of production quantities, right, into a list of total cost. Now, there's no question in the question, so I'm going to make it up. So let's assume you're back to your two products. I think I said bacon and clocks. One time I said, I think one time in a previous semester, I said your two products are bacon and cats, and somebody didn't like that, so I made sure I changed it to clocks. Now, let's assume your production vector is the following. All right, so look, here we go. So there is your production vector. So 10, 20. Now what we want to do is we're gonna find t of x, and then we're gonna come back and understand what this just did for you. Okay? So hey, let me ask you a question. How much money are you spending in production of your bacon and clocks? Do you know? Are you awake right now? Well, x sub 1, we have a 10. X sub 2, we have a 20. So you are spending 10 plus 20, you're spending $30 worth of production. Right? There's $30 worth of, you're throwing $30 at this little project of yours. And so now we're going to see how much of that is going to be ate up in costs in just a second. Ready? So t of x. So since we're gonna use this x sub 1 multiplied by that vector. So this would be x sub 1 multiplied by, now this is 0.45, 0.25, 0.15 plus x sub 2 multiplied by 0.40, 0.30, 0.15. All right, ready? So what I'm doing is I'm simply dragging and dropping my x sub 1, x sub 2 for this particular production vector. So I'm going to have 10 times, and you'll have to entertain yourself for just a second. Plus 20 times 0.40, 0.30, 0.15. All right, here we go. So if we distribute our 10 into that vector, distribute our 20 into that vector, and then take the sum of that, so we would have 4.5, 2.5, 1.5, plus, let's see here, 20 times 0.4, so it's 8, times 0.3, 6, 15% of 20, 3. I think I did that right. Yeah, I think I did that right. Okay, so now let's take that sum, and we end up with the following. 4.5 plus 8 is 12.5. 2.5 plus 6 is 8.5. And finally, 3 plus 1.5 is 4.5. Now, I promised you that after we did the work, we'll come back and figure out what the heck you just did. So let's establish that you had an idea, you had a dream, right? You had an idea, and you were willing to throw $30 at this idea of yours. $30 worth of the production of bacon and clocks. Now, that particular $10 into the bacon category, $20 into the clocks category, and this, after running through that matrix operation, what came back out? Well, overall, in total, you're going to end up spending, out of that 30, you're going to end up spending $12.50 on, let's see, was that materials? Yep, that's your total cost of materials. $8.50 is going to be your total cost of labor, and $4.50 is going to be the total cost of your overhead, right? So add that up. So we got $12.50 plus $8.50 plus $4.50, so that's $25.50. So here we go. $25.50 is going to be ate up in costs out of that $30 and that you put into production. Okay, we're going to conclude. You guys take care.